In this class, we will discuss on a new chapter, that is Clapeyron's three-moment equation. Otherwise called moments of three-moment equations. Actually, in this, a continuous beam has to be analyzed. What is a continuous beam? A continuous beam is a beam which is supported more than two supports. And if it is supported more than two supports, then it is called statically indeterminate beams. Statically indeterminate and what is statically indeterminate beams? There is a difference. What is the difference? Statically determinate beams. In these beams, we can analyze and we can get the solutions of reaction. We can completely solve the beams by using statically equilibrium equations. Statically equilibrium equations is nothing but the summation of all the horizontal forces that are equal to 0 and the summation of all the vertical forces are equal to 0 and sum of moments about a particular point is equal to 0. So, by using these three equations, we can analyze, we can completely solve the problem of beams that is called statically determinate. If it is not, we cannot able to solve the problem by using these equations, equilibrium equations, then that kind of beams are called statically indeterminate beams. What are the different types of beams that are involved in statically determinate beams? Simply supported beam. A simply supported beam is a beam where the supports are acting at the two ends, one at the left end and another one is the right end. Only two supports. So, number of supports are 2. We can easily solve the problem by using statically equilibrium equations. And a cantilever beam where one time only one support is acted upon, either left or right. That is nothing but one end is fixed, another end is free. A fixed support is acting on the continuous beam. And if it is a continuous beam where the supports, the number of supports are more than 2, it's a continuous beam. So, we cannot able to solve by using the equations, statically equilibrium equations directly. So, we are needing of excess equations because number of unknowns are more than 2. So, one of the methods to solve the statically indeterminate beams is called the Clapeyron's three-moment equations, Clapeyron's theorem of three-moment equations. Let us see here. It is a simply supported beam and one more support I am giving here. So, A, here is B, it is C. So, totally 3 supports, a continuous beam called, where the number of the type of loads acting on that. Let us take here this UDL, that is uniformly distributed load, and here the intensity may be varying. I will tell you. Okay. Here it is 2 kilonewton per meter, the intensity of load. Here it will be higher than that of this one, 4 kilonewton per meter. So, we will have two regions, one is AB and BC. Here the span of the AB I am taking as L1 or I am taking as A, here it is B, and the total length I am taking it as L is the span of the total continuous beam. How to analyze this continuous beam? That means you have to find what is the reaction at A as well as at B as well as at C, and what are the bending moment about all the points. We know that this end moment as well as this end moment both are simply supported, it is not a fixed support. So the moment about point A is equal to 0, it is defined defaultly we can say, as well as moment about C is equal to 0. So one and only thing is the moment about point B, how to find, what is the procedure to solve this moment point B. And here, after finding this moment, what about the reaction? What is RA, what is RB, and what is RC? These things to be solved. So the method called three moment equation method we can solve. What is the three moment equation? That equation, general equation, by having the assumption of this support, all the support A, B and C, they are not sinking, they are remains the same level, that is, it is purely horizontal. Supports are at same level, there is no deviation. This is an assumption. And the second assumption is the flexural rigidity. The flexural rigidity is nothing but what? EI is the flexural rigidity, where E is the Young's modulus of the material and I is the moment of inertia. The moment of inertia depends on the cross section of the geometry. So the I is constant throughout the span of the beam. So EI is constant throughout. Mistake. By having these two assumptions, we will have a common equation called three moment equation, where the moment about point A, point B, point C, all the 3 points to be covered. The general equation is MA into, so I am taking here the A, so instead of A I will take this as L1, this is L2. So MA into L1 plus twice MB into L1 plus L2 plus MC into L2, because this MB, point B is the bridge of the section AB as well as BC. So this L1 and L2 will involve here, plus 6 into A1 x1 bar divided by L1 plus 6 A2 x2 bar divided by L2, that is equal to 0. So this is called Clapeyron's three moment equation. So by having these two assumptions, I am simplifying the equations. Okay, MA into L1 plus 2MB into L1 plus L2 plus MC into L2 plus 6 into A1 x1 bar divided by L1 plus 6 into A2 x2 bar divided by L2. So here this is called moment at point B, moment at point C, L and L2 is represented here itself. And the unknown things are this A and X bar. What is A and X bar? Here A is called area of the bending moment diagram. So A refers A1 means this is the first section. AB is referred as the first section or first interval. So here what is the maximum bending moment we are getting? The area of the bending moment, maximum bending moment diagram. Okay, here itself I can take area of maximum bending moment diagram. Okay, so if you are getting the geometry, we can find easily the area as well as x bar. X bar equal to is nothing but is the centroid of the given geometry. Okay, now the same thing I am drawing. So here it is 2 kN per meter, say it is 4 kN per meter. This is a UDL. This A, B is a portion of UDL. So the bending moment diagram will be, the diagram will be like that. It's a parabolic curve. It's a parabolic curve, as well as here also the UDL. So it is also parabolic curve. So the height will indicate the maximum bending moment value. So here it is also. Now find what is the area A1 and A2. Since it is a parabolic curve, this area will be, for a parabola, the area will be 2 by 3 into B into H. So B refers the base. So here the diagram for AB section, the base is nothing but what is the thing is called L1. Okay, and H refers the maximum bending moment value. Okay, so finally for this geometry I am getting the area value as 2 by 3rd of B into H. If it is A1, it is B1 into H1. If it is A2, it is same thing, 2 by 3rd of BH. And for the second region, BC region, it is B2 into H2. So here base is nothing but what is that one? B1 equal to L1, B2 equal to L2, and H1 and H2 are the maximum bending moment values. And the centroid is nothing but, here I am getting the centroid. So here this is called x bar, and in this section this is x bar. So for the first region x1 bar, this is x2 bar. Let's have, this is the two regions. Okay, in these two regions, this is left side, so the centroid will be measured from the left hand side, from the left to right, as well as in this region, this is in the right side, so we can take the centroid to be measured from the right to left, x2 bar, not left to right. So this is depends on the geometry. So x1 bar and x2 bar, here x bar equal to L by 2 for this kind of thing. So in that, what is A1 and A2 and what is B1 and B2, okay, then x bar. So here we know what is moment at A, moment at B, moment at C, what is L1, what is L2, and now the remaining things. A is the area of the maximum bending moment diagram, A2 is the maximum bending moment diagram for the particular region, and x bar and x1 bar and x2 bar are the center of the particular region from where it is measured. I have shown here itself. Okay. Now let's solve one problem.